Howdy everybody, Mr. Mark with you, and in this video we're going to investigate vertical circles. Like what happens when things are moving up and down and in a circle, and we can't just ignore gravity. In these cases, there's many times multiple forces that are either working together or working against each other when things are turning. So let's start with a simple review and then look at some specific examples and work to an understanding of how gravity and other forces can cause things to turn. So let's start by reviewing. A centripetal force is a force that is directed towards the center of a circle and causes a thing to turn. And most of our examples so far have been simple things like a car going around a curve where there's a single force that really matters. For a car, it's friction, and the car's frictional force is pointed towards the center. We saw that the frictional force is centripetal, or center seeking. It can be set to the quantity mv squared over r. If we look at this from a vertical perspective, like from behind the car, we still see that friction force going towards the center of the circle, but we also have to remember that there's a gravitational force going down and a normal force going up. These don't affect the centripetal motion of the car because they balance each other out and give us a net vertical force of zero. But let's see what happens when things move vertically and that's not the case. Here's a good example of a vertical circle. Some riders going around a vertical loop on a roller coaster. In this situation, there are two forces that are pushing on the riders. The first is the force of gravity, which is always there pushing down. And then the second would be the force of the seat pushing on the riders. For the roller coaster as a whole, it's the track causing the roller coaster to turn. So in this case, what forces are causing the roller coaster to turn and how are they working? So if we were to draw a free body diagram of the forces on our roller coaster, we would see that gravity pushes down and the normal force also pushes down. Since these two forces are in the same direction, I'm going to add them together, like make down the positive direction so they both have the same positive sign. And then because they are working together to turn the roller coaster, as in they are both centripetal, I'm going to set the sum of those two forces equal to the quantity mv squared over r. So to make this example a little bit more concrete, let's suppose that we have a rider whose mass is 45 kilograms, and they go through the top of that loop at a velocity of 16 meters per second. If the radius of that loop is 18 meters, which is a reasonable radius for a roller coaster loop, what force does the seat exert on them? So we can take our equations that we just generated. The sum of the forces is Fg plus Fn, and together they are centripetal, or mv squared over r. So we can set Fg plus n equal to mv squared over r. Solving for Fn, just subtract Fg from both sides. I would get Fn equals mv squared over r minus Fg. And then if I substitute in all those numbers, mass of 45, a speed of 16, radius of 18, and then G, round that off to 10 newtons per kilogram, then I get a normal force in this case of 190 newtons. So notice that that is smaller than the weight of our riders, and so they don't feel as large a force pushing from the seat on them as they normally would if they were just sitting on the seat at rest. So what if our riders were going a little bit slower? So let's take that speed and drop it to 12 meters per second and see what happens to the normal force. Using our same equation, Fn equals mv squared over r minus Fg, let's substitute in that new speed of 12 meters per second. The first term would be 360 newtons. The second term would still be 450 newtons because the weight of the rider wouldn't change, which would give us, if you think about that real carefully, a negative number. Now, the normal force can't be negative. The seat has to be pushing down. If it wasn't pushing down, it'd be a different situation. And so this situation, as we've written it, isn't possible. Like I can't just make up a speed for this roller coaster of 12 meters per second. These people would fall instead of moving in a circle. Kind of has some important consequences. So let's investigate further. The smallest the normal force can possibly be is zero. Like the normal force can't be any smaller than that. So if we take our equation and calculate the speed that would give us a normal force of zero, we can figure out how fast we'd have to be going just to make it through the loop. So take our equation, set the normal force equal to zero. In this case, since I now have m's in every term, I can cancel them out, and I can solve for the velocity. So multiplying both sides by r, taking the square root of everything, substituting in g and the radius of our loop, gives us a speed of 13.4 meters per second. So what that means is that we have to go at least 13.4 meters per second in order to make it through this vertical loop. That gets us through. If we were to go slower, let's just say 8 meters per second, we can't change how big gravity is. It's always going to be there. So that's something that's going to fall instead of moving in a circle. That's not really a desirable situation for people riding on a roller coaster. So it is important to realize that there is a minimum speed through which things can move through on a vertical loop in a roller coaster like that. We're going to investigate a second example, kind of the other way, car going over a hill in just a minute. So let's look at another example. Suppose that now the roller coaster was at the bottom of the loop, and we wanted to know how fast the roller coaster could go in order to keep the normal force less than 5 times the weight of the riders. So if you've ever been in a roller coaster, you know at the bottom you kind of feel real heavy because you're accelerating towards the center, and the normal force is in the opposite direction as gravity, and you can get to a point where that force is too large. So suppose we want to limit that force to 5 times the rider's weight, which is quite a lot. Let's figure out how fast we can go. So our free body diagram would have gravity going down, and it would have the normal force going up. I've drawn the normal force larger because I know the net force needs to be upward because that's where the center of the circle is. Together, these forces need to be centripetal. So the sum of the forces in the y direction is the normal force minus the weight, and that quantity is still equal to the quantity mv squared over r. Together, that is centripetal. So I'm going to replace Fn with 5 times Fg because that's the condition that we're after here. Keep it to 5 times the rider's weight. And so if I do a little subtraction there, that would give me 4mg. So we need mv squared over r to be 4mg, and that'll tell us the maximum that this speed can be. The m's cancel out, same for all the riders. And so I get something like v equals the square root of 4, in this case, r times g. So if we substitute in those numbers, again, 18 meters for our loop radius, we get a velocity of about 27 meters per second. So if I exceed 27 meters per second on the bottom of this roller coaster, my riders are going to feel a larger normal force than 5 times their weight. And that's kind of about when the point where you're starting to experience things like tunnel vision and blacking out for people riding on roller coasters. So it is something we want to consider when we design a roller coaster. So let's look at another interesting example, which you've all probably experienced, and that is a car going over a hill. And if you drive over a hill at a normal speed, you simply go over the hill. But if you drive over the hill at a large speed, the hill can potentially become a ramp. It's pretty common for cars to be going too fast over a hill, and they may not necessarily fly off into space like that, but they can lose grip with the road and lose control and start a collision or something like that. So what we're going to do next is we're going to figure out how fast a car can go over a hill before it loses contact with the road surface and either becomes a projectile or does something else undesirable for cars. So let's draw the free body diagram for our car on a hill. Obviously, gravity pulls it down, kind of like always, and then the normal force pushes up. So if we kind of consider these forces and what they do, we can derive an expression for how fast the car can go over the hill before it loses contact with the hill. I'm going to set down to be my positive direction because that's the direction that the car is accelerating in. towards the center of the circle. And so I get something like Fg minus Fm. I know that the normal force has to be smaller than gravity because the car is going to accelerate downward. It's turning towards a point that is below the hill, not above the hill. And because the car is turning, I can set the sum of the forces equal to the quantity mv squared over r. Now, the smallest that the normal force can possibly be is 0. And so if I set the normal force equal to 0, I get mg equals mv squared over r. I can cancel out the m's, and then I can do some algebra and end up with something like v equals the square root of g times r. Notice that the bigger r gets, the bigger v gets. So if I'm designing a roadway and I've got hills on it, I need to be careful about how big a radius those hills have. If the radius gets too small, then I run the risk of cars that are driving on the road going so fast they lose contact with the road surface. And so in places where that's unavoidable, like in the mountains, for example, and the radius of a hill is kind of tight, then I need to have some, signs and things like that to indicate, hey, you need to slow down before you go over this hill. And, maybe it'd be helpful if we put the free body diagram on there so that people understood like why you have to slow down when you go over the top of this really steep hill. So let's kind of review what we've learned today. You can have multiple forces on things that are turning that are acting in the direction or the opposite direction of the acceleration. And so, just like always, when there are multiple forces involved, draw a free body diagram, write a net force equation. In this situation, the sum of the forces would be centripetal. So you can have something like the centripetal force is gravity plus the normal force. If it's something on a rope, it could be tension plus gravity or something like that. And then don't forget that gravity exists. It can be part of the equation, and a lot of times it's an important part of the equation. We'll work on this during class next time. I'll see you then. Ta ta.